I want to begin my presentation with a statement of Geoffrey Hinton, one of the godfathers of modern deep learning, who stated almost 10 years ago, people should stop training radiologists now. It's completely obvious that in 5 years deep learning is going to do better than radiologists. Fun fact, it's still not true. So today I'm your guide in a world of healthcare and medical computer vision, and we'll try to figure out why that happens actually. Before we proceed, some disclaimers. The speech gonna be focused entirely on medical images and computer vision on them. We mainly focus on open source models and contribution. I'm not a doctor at all. By the way, if there are any doctors here, raise your hands. Thanks God for this present. And anyway, I have around 9 years working at medtech or biotech domain, so I know some stuff about this as well. So, why do we need actually AI for medical domain? There is a cool study about CT lung cancer screening on chest CT scans that showed that around 77% of cases could be diagnosed earlier. Like 54% were just missed, and 23% were basically diagnostic errors. And this is a good example of where technology actually could help us in healthcare. So, let's go deeper, the uglies. Adoption of AI, especially in healthcare, is kind of story of failures. For example, I will just keep this boring slide that's basically stated that all companies say that they have 99% accuracies, and when they deploy it, we see that accuracy actually way lower than 99%. Here's a cool story about computer-aided detection for breast cancer screening. In 2002, FDA-approved CAT system were first deployed for breast cancer screening in the US. And what we see here that CAT basically, implementing of CAT leads to decreasing of accuracy of detection. With like radiologists with CAT works worse than without CATs. We see the similar detection rates with CATs and without CAT as well, but fun fact that this stuff costs around $400 million a year, and it still costs, by the way. So just imagine, like, the folks throw money without any outcome. Another example of failure, it's Google AI. Somewhere around 2016 or 17, I don't remember exactly, they presented a state-of-the-art model for diabetic retinopathy detection. That's basically a retinal disease linked with diabetics. And in order to diagnose this, you need to take a fancy picture of your eye. And because it's like a picture, we can feed it to a computer vision model. Again, it's like 2016 or so. It's after deep learning revolution without AlexNet, ResNet, all this stuff appeared. So there were a lot of expectation around we are going to solve this problem quickly enough. So they built the model, they deployed it in Thailand, and like 21% of the images were rejected by the system because of low quality. And on the rest, performance was like just unusable, basically. Another example here is a like fail of all failures. It's Watson AI, Watson Health, IBM solution. There were a lot of rumors and expectation about these models, and basically stated that, okay, we're gonna create a revolution in healthcare. Our system gonna be capable to provide state-of-the-art personalized treatment for like our patient, taking into account the newest discoveries, like all this stuff. Like 7,000 employers, $4 billion of investment. And professional reaction was something like unsafe and incorrect, or my favorite one, the product is a piece of shit. You can say that, okay, Ivan, you're talking about outdated technology. It's like almost 10 years old. But here is a plot twist, a case study. Google recently released MedGemma LLM and Vision LLM, specifically trained and fine-tuned to handle healthcare-related tasks. I picked a random patient from a public data set about COVID-19 cases. Like here is several images from these CT scans. Like you can get that there is something wrong with the patient because like we usually don't put a tube inside the patient when the patient is perfectly fine. So there is something off here. And I run this case through multiple LLMs, and what we got here. Like MedGemma yelled nothing. MedGemma believed that this patient perfectly fine and healthy. No pathologist, no sign of any disease. Like 100% healthy patient. Okay, what could one of the most capable closed-sort LLM give us? Like here is the long list of findings here, like lung nodules and masses, liver abscess, like a lot of mass here and there, problem with bones, like basically tons of like illnesses here. And I asked my old friend of mine, Polina, who is really experienced radiologist, to review this report. And to sum up, it's like that's a lot of bullshit. Basically, that's 100% pure hallucination. If you ask more recent models like M3D, it's a model specifically built to handle CT scans with 3D image encoder. Again, specifically built to handle CT scans. Again, this will hallucinate really heavily. Like, fun fact that the model closer to the like normal report, let it be in this way, going to be LavaMed, one of the first medical-related LLMs in the open source, but still this model hallucinates pretty heavily. Why that happens? Like, first of all, the obvious reason here is immature technologies, like CADs based on classical computer vision back in the day. Like, yeah, that's kind of a problem. We also have a problem with data and low-quality data. We are going to cover this topic in details a bit later. We also have domain gaps between training data and real-world data. That's a case for Google's diabetic retinopathy detection. Also, lack of domain knowledge when engineers don't take into account the domain properties of the data and don't handle it properly, and incorrect evaluation protocols. We're going to cover it a bit as well too. So let's move to the next step, the bet. Here is a cool open source dataset called Leeds Eatery. It's one of the best in terms of quality of annotation dataset for lung cancer screening that you can access without any restriction, basically. And the folks spent around 10 years annotating these data sets. It's only 1,000 CT scans. And the protocol looks like this. First, independent annotation by radiologists. The 4 super experienced radiologists annotated manually each of the CT scans. Then they share annotation with their colleagues and review their results, looking into what other radiologists marked or labeled it in the particular scan. Then formal error detection, basically the special guy come and play and analyzed any formal issues with data formats, labels, and so on and so forth. In 2016 Grand Challenge Luna 16 took place, and after which additional corrections and additional findings were made to this dataset. So, again, almost 10 years, 4 super experienced radiologists, 1 international competition. And what do we have after this? I would like to focus you on these 2 rows here, second and third. In case at least 1 radiologist marked a finding as a nodule, we have 2,600 something cases that at least 1 radiologist labeled as a nodule here, but all 4 radiologists labeled the same finding as a nodule. We have only 928 cases. It means that all 4 radiologists agree with each other around like in 30% cases basically. So we have super low agreement rate here. What more interesting, that the radiologists also disagree with boundaries of the finding. They can say, okay, that's both like a nodule here, but they can outline different borders of this finding as well. So we have a big problem here. Like annotating of medical images is a like super hard process, requires a ton of manual labor, and moreover, it's not just some random manual labor. I mean, we need a trained professional to do this actually. Why not to use self-supervised learning? Here is a trick. Here is a difference between general images and medical images. For example, when we mask a general image with some white squares, we still keep the same semantic meaning for this image. Like when we put a white square here or there, we still like can infer that, okay, that's actually a dog. But when we hide this part of a brain in a red square, we actually change the meaning of that image. It's now a normal brain, like it's not a pathology anymore. We can say that, okay, under this white square, some like pathology hides. We don't have enough information to do this actually. So self-supervised learning in medical domain also is kind of tricky one. Another cool story about data acquisition. Like basically when we're talking about general images, like some, I don't know, any pictures, we basically take a phone, take a picture, okay, we are good here. For medical images, there are specific protocols that describe how we need to position a patient, how we need to acquire the data, and so on and so forth. There is a cool study about folks who gathered data from one hospital with two different X-ray machines, one located in the ambulance, one in the emergency room. And they tried to build a classifier that can help to detect pneumonia, bone traumas, and normal X-rays. They collected data from these two machines, and basically there is a distribution shift between ambulance and emergency room. In emergency room, there are a lot of cases with traumas and other related stuff, and an ambulance usually deals with like pneumonia actually. So, because in the emergency room, there is always a time pressure, patient could be located not exactly how they should be coordinate to the protocols. There is also difference in labels here. Like there is a special object placed on the left side of patient that helps to distinguish left and right on the sides of a patient on an X-ray. So when they trained the model yielded like super nice performance, like as usual 99.9% accuracy. I am exaggerating a bit, but you get the point. In testing the real world data, the model just don't work properly because actually modern model learned how to distinguish data from emergency room from data from ambulance. And thus, the model basically learned a pattern about patient localization, position, and all of this stuff, rather than learn actual patterns about the condition. We also have black swans, obviously. That's back in the day I worked at Botkin AI, and we worked with lung cancer screening on chest CT scans. That's how our data looked prior COVID-19 pandemic. We need to find these small dots here and there. The one with the red circle and this one as well. So, looks pretty simple. And after COVID-19, our data started to look like this. Like imagine finding these small nodules here, like it's kind of hard to do. What more interesting, because of this COVID-19, the patient, how radiologists put a patient inside the machine also changed. Like usually there is a normal patient positioning on their back. They started put them on their chest because it's hard to breathe for a patient, so on the chest it's a bit easier for them to breathe. We also have seen a lot of breathing artifacts. That's sort of motion artifacts in a camera when you, like, I don't know, do a picture with a long long shot picture. So like object can move a bit and create this blurriness. We can observe the same pattern in city machines as well. And yeah, because of all this stuff, like it requires ton of data ton of manual labor to annotate the data and all this like blah, blah, blah. Usually like a data set, especially for LLM training, gathered through scraping the papers, Radiopedia and whatever. Here's a sample from a data set called MedBL Thinker Eval. It didn't took too long time to find this sample. So this is an image that we need to feed into the model, like as is, without any modification from my side. This is a question. What does the green arrow in the image indicate? Even without the option, I bet everyone here can answer, correctly to this question. Like, it's obviously bleeding. We have like this text here. So, like, that's a bit of a problem. So, as TLDR, what we have? Labeling requires ton of labor, manual labor, and actually specifically trained folks to handle this. Radiologists have super low agreement rate with each other. We basically don't have ground truth in medical images. Unfortunately, or fortunately, depending on your point of view, we can just take a patient, put it into the CT scan machine, then slide them into thin slices, put it under the microscope, and actually determine ground truth. We can do this because it's unethical, but anyway, we don't have ground truth. Acquisition process of every data point actually heavily impacts the outcome of this process. And medical image is a bit different compared to like general domain, and it means that we need to take this into account. So what's the bright side of this? Let's talk about the good point of medical domain. So first of all, let me introduce you UNet. Back in the day, before 2015, task about segmentation usually handled by encoder-decoder approach. There is basically a convolutional encoder, there is some bottleneck here, and then convolutional decoder that projects this compressed representation into segmentation map. In 2015, UNet architecture was proposed, and the idea is super simple. Let's add these skip connections between corresponding blocks of encoder and decoder. And thus, basically, each skip connection here serves us as a source of information. Basically, each step here in encoder, like when we downsample our features, we kind of lost some information about like specific patterns, small details, all this stuff. And skip connections between blocks can help us to restore this information. So nowadays, UNet-like architecture is still some sort of workhorse of medical image analysis. You can still Google easily and UNet-like architecture based on, like, put a buzzword here. Still works pretty fine. So let's talk about lung cancer screening on CT scans. We basically need to find this small guy here or there. That's a really small small thing. It could be as small as like 3 or 4 millimeters. It's basically like 5 by 5 pixels object that we need to find inside patient lungs. So it's kind of like finding needle in a haystack, like pretty complicated one. But if we take a look how radiologists handle these tasks, they usually use two tools. One of them is a multiplanar reconstruction. Usually, like CT scan is basically a set of Excel slices. Basically, like this, we acquire data, like cutting the bread in the slices here, like dun, 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 dun. And we can use this sequence of slices to restore other point of views, like sagittal at corner here. Thus, we can like see what actually around this particular area somewhere and try to figure out how it looks in 3D. Another way is a maximum intensity projection. That's actually a super cool tool. Basically, it works like this. We take several slices, like 41, 42, etc. And now we have for each pixel a value from different slices. And we can take a maximum value of it. And thus project all this sequence of slices into one 2D image. In CT scans, it works like this. We can now see all the tissues inside the patient lungs. Why it's actually really helpful, it's because CT scans, pixels values of CT scans, it's not just some random units, it's a Hounsfield units. It's basically density of a point inside the patient body. And the higher value we have, the more harder for X-ray to penetrate through this point. So these bright stuff, it's bones, they're super dense. It means that for X-ray it's harder to penetrate this one. These black areas, it's an air. So basically this region can be penetrated by X-rays without any problems at all. So the denser it, the higher value we have, the brighter value we have. So if we put all this stuff together, we can build a model with this idea, with these ideas inside. First of all, on the overview level, we convert input CT scan into set of reconstruction, axial, coronal, and sagittal, and feed them into our model. But in order to work with maximum intensity projection, we actually want to put it inside the model. Why? Because when we take this maximum projection, tissues nearby the point of interest could overlap with it and basically hide it. So you can just, pre-compute projection in a CT space and feed it to the model as additional input. We want to do it in a feature space. And thus, our model could be some sort of pre-filter that kind of highlight the areas of interest and suppress some, surrounding tissue that no interest for us. Oh, so how we can do it? We basically feed our data into the model, run it through a convolutional lawyer, split it into blocks, take a maximum projection across that axis here and there, and use the output via concatenation. Where to put it inside the model? Here. Oh, I need to go to this site as well. Right here. So we do some first convolutional lawyers, 3D convolutional lawyers here, apply maximum intensity projection inside these features, and then use UNet as usual, because it's medical images. We all use UNets here. And it works pretty fine. With these two ideas in mind, we were able to achieve state-of-the-art result on lung cancer screening, basically with price of just running UNet on a CT scan. It's super efficient in terms of compute and time of processing, but still yields a really good results compared to other models on the market. What even cooler here is that, as I mentioned, maximum intensity projection could lead to missing cases. For example, we have these two nodules here. They're in the circles. I hope you got it. The bottom row, first on the left, is maximum intensity projection of the same scan, and the nodule marked as a green circle basically is hidden by tissues nearby. If we just feed this image to a model, we wouldn't be able to detect this nodule because there is no way for model, there is no information to make this decision correctly. But with maximum projection built in the model, we still can do it. This nodule is still visible even after applying maximum projection inside the model. That's actually super cool. Okay, what next? There is a cool concept here called Kolmogorov networks. That's another way to formulate deep learning models, all modern deep learning models based on multi-layer perceptron idea, which relies on universal approximation theorem, Basically what we have here, we have a fixed non-linearities. We have learnable weights on edges. We now like apply weights to input stream, sum it up, pass it through fixed nonlinear activation, repeat n times. In Kolmogorov-Carnot networks, we do it in a different way. The idea is to like use Kolmogorov-Carnot representation term. Basically, instead of going with fixed nonlinearities, and we use learnable activation functions on edges. So like here on each edge is a separate learnable nonlinear function. In the original paper, they proposed to use splines. You can use any other learnable nonlinearities you would like polynomials and whatever it could be. And only one fixed nonlinearity after summing up all these results of learnable nonlinearities. Super cool idea, super fancy. Fun fact that it works super, okay. Before we proceed to a cool part that it works super fine in medical domain, first of all, I want to introduce to you one more version of UNet. It's U²net. Basically, the idea to like train an infer UNet while you train an infer UNet. So instead of going with usual convolutional blocks here and then like do downsample and repeat n times, we can just put a really UNet instead of these convolution layers. Like each block here is a small UNet that do downsampling, upsampling, skip connection stuff. We stack them multiple times and it works actually super fine. There is only one problem. You need to like spend a lot of compute and GPU memory to make it work, but it works super cool, like really nice stuff. So if we just replace all convolution layers here with Kolmogorov-Carnot convolutions, we can get results way better than like traditional convolutions instead. Like again, works super cool and especially works cool because all these data sets, it's low data data sets, basically like several thousand of samples per each data set, and like it works perfectly fine, way better than traditional versions of UNets, U²nets, and other options of UNets, basically. Which is, from my point of view, super cool, because in a general image domain, I haven't seen like breakthrough around Kolmogorov cans. Okay, let it be in this way. I can say Kolmogorov-Carnot one more time. Sorry for that. Usually performs on par with the current state of the art, like transformers and so on and so forth, but it works super cool in medical domain. So, what we can learn from this information? First of all, explore and exploit domain properties. It's super important, especially in medical domain, because all options of data acquisition, like, I don't know, ultrasound, MRIs, CT scans, whatever it could be, like they all have their properties and we need to take them into account. Medical imaging still a low data domain, like because it's hard to acquire, hard to share, and because of like legal stuff as well. Like open source data set are pretty like small, actually, to be honest. I recently did a cool stuff. I just scrapped all publicly available CT scan data set. And I got, who can guess how much data points I acquired after this stuff? 200 what? Just 200, so 200, no, a bit. 10K, 10K I have heard. Who more? 50K, okay. Sorry? All available at the moment, like I don't know, like all available CT scan data set in the internet right now, open. 20,000? Just 20, okay. After all this process, I got 75,000 CT scans, valid CT scans. I want to like highlight this. Only 75,000 of data points. That's actually Compare it to, like, I don't know, general images when you can easily acquire billions of images, like, that's a problem. So don't hesitate to try out new model architectures and new model approaches, especially in the medical domain. For some reason, it works pretty fine. Like, there are tons of CAN options, Mamba-like, CAN Mambas. Like, basically, you can pick any buzzwords here and apply it there, and probably they would work somehow, sometimes even better than traditional options here. So, like, I don't know, be mindful about applying general image techniques in medical domain. They usually needs, let's say, tweaking at least. And yeah, be careful about evaluation. So, I want to share my bets here. Like, I mean, there is obviously some trends here and there where the entire area of CV on medical images heading right now. From my point of view, three important areas. Here is multimodal approach. Basically, what we want is to build a one encoder model to rule them all. I mean, all available image modalities. But okay, let's be realistic. Let's solve this at least for one single image modality. Let's say for CT scans or X-rays or MRI, whatever. Even with this limitation, it's a pretty challenging task because of, like, a lot of problems and properties of this data we need to take into account. Second point, text-to-image models as a data source. We basically limited in terms of data available right now. Even for giants like IBM or Google, it's still challenging to acquire large-scale data sets. So building reliable and good enough text-to-image models could help us here a lot. And tools for semi-auto labeling and semi-automatic region proposal and all this mask segmentation, blah, 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 could help us to reduce amount of manual labor needed to create this data set. And the super final takeaways, like, even if you don't work in medical domain, there is some, let's say, personal experience I would like to share with you. Like, take into account always domain properties, and basically domain experts are your best friends ever when you're doing, like, I don't know, train a new model for some domain or some task or whatever it could be, because these folks usually a good source of insight to approach to this task, how to handle it better. Don't forget about GIGO, garbage in, garbage out. I probably have shown to you that even in a medical domain that happens. And I encourage you to experiment. Sometimes the best results emerge from the really crazy ideas, and why not to try it? Thank you very much. Useful links. Okay, I forgot. In case you're interested in this, here is the links to a data set. Three recent data set with CT scans, like relatively large one. It's about 50K. As you can imagine, that's basically 60% of what I acquired during my run here. And some tools that could help you to join the field. Thank you very much. And if you have any questions,